Hi, in the previous video we have been talking about rotations. So we have a subtree on the left and we are able to make a rotation. We just have to rotate the root node, which is the node D, and after the right rotation the root node is going to be the B, and the B's right child is going to be the previous root node. If we make a left rotation on this right subtree, we are going to end up with the subtree we have started. Okay, but let's specify the concrete situations. We have the case 1. This is the so-called doubly left heavy situation where we have a root node and the root node has a left child and this left child has another left child. For example, the root node is the node D, then the node B and the node A. So we have to check the height parameters. What about the leaf node? This is what we have been discussing in one of the previous videos, that the null pointers, so if a given node hasn't got any children, then it's going to have basically a null left child and the null right child. And we assign the height parameter -1 to these null values. The difference between -1 and -1 is 0, so this subtree basically is balanced. What about the node B? The node B doesn't have any right child, so it is a null pointer or null reference, and it has the height parameter -1. The left child of node B is the node A. It is a leaf node, and we assign the height parameter 0 to all the leaf nodes. The difference between the two of them is equal to 1, so we don't have to make any rotations. What about the root node? We know that the A is a leaf node. It has a height parameter 0. The B has a height parameter 1 because we just have to increment the node A height parameter. And we know that the right child of D is a null pointer, so it has the height parameter -1. Okay, so the D has a left subtree with height parameter +1 and the right subtree, okay, it is a single null pointer, but whatever, it has the height parameter -1. The difference of the height parameters is more than 1, actually it is 2, so we have to make rotations to the right. And we just have to rotate it to the right. As you can see, in this subtree, the root node is the D and the left child of the D is the node B. After the right rotation, the left child of the root node is going to be the new root node. So that's why the new root node is the node B. And the right child of this B is going to be the previous root node, which is the node D. So this is how we make a right rotation on the node D. Okay, so this is the case 1, the so-called doubly left heavy situation. In this case, we just have to make a single right rotation on the root node. It's very important that we are not done, in the sense that we have to check that whether with this rotation there may be other violations of the AVL property in other regions of the tree. So we have to check it until we get to the root node. Okay, so what about the source code? Basically, this rotate right is quite easy to implement. We just have to update the references. We create a temporary left node, so we get the root node basically as a parameter, this node. We get the left node and we store it in a temporary left node variable. We get another node, the so-called T. It is the temp left node that get right node. And the temp left node.setRight node is basically when we make the left child of the root node to be the new root node. So if you may recall, in this case we have the root node, which is the D. We get the left child, which is the node B, and we set for this node B to have the right child as its parent, so the D. So this is how we make the rotation to end up with this situation. And of course we have to update the height parameters because it has changed according to the rotation. Okay, what about the case 2? It is quite symmetric, so this is the so-called doubly right heavy situation. We have to do approximately the same as we have seen for the case 1, but on the opposite direction. So we have to make a simple left rotation on the root node, so on the node B. But let's check whether it is a valid AVL tree or not. The E has a left null child and a right null child. Both of them has the height parameter -1. It is okay. What about the D? We have the left child with height parameter -1, and because E is a leaf node, it has the height parameter 0. Okay, it doesn't violate the AVL property. The difference between the height parameters doesn't exceed 1. What about the root node? Again, we have the left subtree with height parameter -1 and the right subtree with the height parameter +1. Okay, the difference of height parameters is more than 1, we have to make a rotation. And we just have to rotate it to the left. So the B, in this case, this is the root node, it's going to be the left child of its right child. So the B's right child is the D, it's going to be the new root node. What about the pseudocode? We just have to do the same approximately, but instead of the left child, we have to get the root node right child, and we have to set this temporary right node, set left node to be equal to the previous root node. This is how we update the references, and of course we have to update the height parameters because it may change. Okay, what about the case 3? We have this so-called left-right situation when the root node has a left child and this left child has a right child. It's very important that these nodes may have left and right children, but it doesn't matter because we do not modify the pointers for them. For example, B can have a left child, but it doesn't matter because if we change the reference for the B, then its left child is going to remain the same, so we don't have to bother about it. Okay, let's check whether the AVL properties are violated or not. The difference between the left child height parameter and the right child height parameter does not differ more than 1, so it is okay. What about node B? It is okay because the difference between -1 and 0 is equal to 1. It's not greater than 1 and it's not smaller than -1, so the difference is smaller or equal than 1. Okay, what about the root node? We have the right child with height parameter -1 and left child height parameter 1. Okay, we have to make some rotations. First, we have to make a left rotation on the node B. Okay, as you can see, the B is going to be the left child of the node C, and the node C is going to be the left child of D. But this is basically the doubly left heavy situation, so we just have to make a right rotation on the root node. Okay, and this is how we make it balanced. As you can see, in the beginning we have this situation, we just make a left rotation on the B, then we make a right rotation on the D, so the root node. Okay, this is how we end up with this situation. C has a left child B and a right child D, and it's going to be balanced. What about the case 4? It is quite symmetric, so instead of the left-right heavy situation, it is the right-left heavy situation. And it's also important, as we have discussed for the left-right heavy situation, that these nodes may have left and right children, but it doesn't matter because we don't modify the pointers for them. For example, if we have a right child for the node F, we are not going to bother about it. No matter what's going to happen to node F, the right child of F is going to remain the same. We are not going to modify this reference, so we don't have to bother about it. Check whether the AVL properties are violated or not. -1 and -1, the difference between the height parameters is 0. Okay, let's consider the node F. The difference between the height parameter doesn't exceed 1. What about D? We have the height parameter -1, height parameter 1, so we definitely have to make a rotation. First we have to rotate the F to the right, and then it is the doubly right heavy situation, so we have to rotate the root node, so the node D to the left. Okay, and this is how we end up with a balanced situation. I don't want to repeat myself over and over again, but why is it good to make rotations? Because we make sure that the tree is going to be balanced. Why is it good? Because the logarithmic time complexity for most of the operations are going to be preserved, and this is exactly what we are looking for. A balanced tree, no matter it is an AVL tree or a red-black tree, is quite predictable. We know for certain that the operations are going to be ortho-log time complexity, in worst case, best case, no matter what. Okay, so that's all about the 4 cases. Thanks for watching.